Hello, folks. Welcome. Thank you for being here for our planet weather webinar, or webinar as we call it around here. My name is Dr. Hansi Singh, and today we're going to be speaking particularly about heat, specifically heat, extreme heat, and its impacts across industries and our ability to predict it. So, to introduce myself, Dr. Hansi Singh, founder of Planet AI. I'm an Earth Systems scientist. I also used to be a fellow at the US Department of Energy, and I was formerly a professor. I started Planet because I really wanted to bring some awesome information from the research world to the real world regarding the Earth system and how it's changing and how we can adapt to it in order to help industries, businesses become more resilient. And so today in particular, we're going to be talking about heat, which is something that we would all like to be more resilient to on our rapidly warming planet. So what we'll be talking about today is, first of all, the physics of heat and heat waves, heat on a warming planet. We'll talk a bit about the impacts of extreme heat, including on health as well as on economics. We'll talk specifically about the 2021 Pacific Northwest heat wave, which was definitely a black swan event type of heat wave. It was rarer than one in 1,000 years. We'll sort of go into some of the details of that particular event. And then we will talk about some long range predictions of heat. So we'll go a little bit into the long range weather forecast and tell you a little bit about what to expect over this coming summer. We specifically scheduled this at a time that was really timely because we're about to get into the hottest months here in North America, in Europe, basically, the Northern Hemisphere extratropics. So hopefully this is very relevant for a lot of folks. So first of all, I probably don't need to say this, but one of the reasons why we are feeling the heat is because our planet is getting warmer. So global mean surface temperatures have already risen by about 2.7 degrees Fahrenheit or 1.5 degrees Celsius compared to pre-industrial temperatures. Here you can see the global mean surface temperature and how specifically since like the 60s or so, it's been rising at a relatively rapid clip. And so, in the context of these increasing surface temperatures, we frequently beat records. And so this is for 2025. The dark red color means that that region experienced record warmth. In other words, that year, the year 2025, was a record-breaking year. And you can see that most of the globe is at, much warmer than average conditions. This is just, this is the trajectory we're on. And so we're going to see more and more of this record-breaking warmer than usual or much warmer than usual conditions. It's not even quite meteorological summer yet, and we're already breaking some records. So you may have heard in the news that there are major heat waves going on right now in Britain and France. These are unprecedented temperatures for the month of May. And yeah, it is making the news. It is making travel challenging. It is making people's lives challenging because many of these countries do not have air conditioning systems. And yeah, this is a picture from our forecasting engine, and these much warmer than usual temperatures are projected to continue into this coming week. And I will show you the forecast for Europe for this summer later in this talk. And in general, we can expect over this region much warmer than usual conditions. So it's important to remember, why does heat matter? It matters because it's deadly. Around the world, about 500,000 people die each year due to heat-related mortality, and this is probably an undercount. Heat is especially dangerous for children, for seniors, for pregnant women, And there's many signs of heat illness. Please take note of these if you're going to be doing outdoor activities this summer. Elevated body temperatures, rapid heartbeat, dizziness, nausea, vomiting. If there's signs of heat illness, like please, please, please get help. The rates of death in the US, in US states, tend to be higher in the South and specifically the Southwest. So Nevada, New Mexico, or sorry, that's not New Mexico. Nevada, this is Arizona. I'm sorry, this is New Mexico. Have the highest rates, and some of these other states as well, including New Mexico, including Oklahoma, also have very high rates as well. And that makes sense because these are areas that over the summer tend to have very high temperatures. I'm also going to say, cold also causes a lot of deaths. And so as deaths from cold go down, deaths from heat are going to go up because, our planet is warming. Impacts of extreme heat, it's important to remember, are not just due to temperature, but they are also due to humidity. It is a mix of the heat, the temperature, plus the humidity that can be really, really, really dangerous. And so essentially what we do is we calculate something called a heat index, or sort of the more meteorological, nerdy way to do it is something called the wet bulb temperature, which you might have heard of more often these days, but more or less, both of these take the heat and the humidity into account. Though wet bulb temperature also accounts for some impacts of solar radiation as well as winds. And so what you can see here is that we take heat and humidity into account. The more humid we are, generally, the higher the heat index for a given temperature. And if we're in this kind of purple or red region, this heat index can be very, very, very dangerous to human health. And the reason why is because when we have elevated temperatures combined with high relative humidity, it just means that sweat cannot evaporate. And so therefore your body's normal cooling mechanisms don't work as intended. Heat can also drive economic losses. The reason for this is because workers generally are just less productive when it's really hot. Heat can damage crops. Heat can increase morbidity from many, many causes. And these impacts are large in regions that are already temperate or balmy. So this is a paper by Callahan and Mencken from 2022. And after this paper, this is when they published their famous paper on El Nino and its impacts on economic growth. And so what they did was an economic analysis combined with essentially heat, temperatures that were standard deviations for certain periods of time beyond what was normal. And so what they found is that for every standard deviation in temperature, standard deviation of increase in temperature, they found that there was a marginal effect on economic growth. And so generally speaking, the areas of the globe that are already warm, they see a decline in economic growth. But for areas, for example, that are quite cold and therefore their economies, maybe are growing slower because of the cold, as soon as you increase the temperature a little bit, their economies grow a little bit faster. So you can really see the US is in this like very in-between zone where there might be some parts of our country that do better as, temperatures warm, but there's other parts of our country that are going to be doing worse. And you can see really that these effects are focused in the tropics. This is a map showing particularly the impacts of heat on economic productivity using the gross value added by workers. And so today, the estimate is that heat leads to the losses of about 100 billion in economic productivity. And it's estimated that as our country grows warmer, that this number is going to grow. So by the 2030s, we estimate that this will be in, 200 billion or so, if we're not able to adequately adapt to this heat. And this is most important for at-risk jobs. So this includes agricultural work, which is predominantly done outdoors, construction, as well as jobs that perhaps are not very well climate controlled. For example, that might include retail warehousing. Now, heat waves have a very specific definition. So, in the context of heat or extreme heat, a heat wave is a very specific span of time, usually lasting 3 days or more, where our temperatures are much higher than usual at that location. And so usually we define this as a couple standard deviations. Sometimes, we might want to be even more stringent with it. One way that we sometimes define this is how often is an event like this going to happen over, say, the course of 10 years, over the course of 100 years, or 1,000 years? And by looking at that, we can gauge how extreme that particular heat wave event is. And the final ingredient usually is defined in terms of how hazardous the event might be to human health. So one way of thinking about that is the heat index above 85 degrees Fahrenheit or 95 degrees Fahrenheit. In some regions, for example, I live in the Pacific Northwest. A lot of our households here don't have air conditioning. And so, 85 degrees might seem like nothing if you're in Texas, but if you're here in the Pacific Northwest and you don't have air conditioning, then, a temperature of 85 or 90 is going to feel pretty extreme, especially if the temperatures don't go down overnight and your body is not acclimated. So this is one element of a heat wave that is particularly dangerous. It is a shorter span of time where the temperatures are really high. And so because it's a shorter span of time where the temperatures might be much outside what is usual, our bodies have not had the physiological opportunity to adjust and adapt to those temperatures. And so it makes these episodes particularly more dangerous. How do heat waves happen physically? So it starts with meanders in the jet stream. So here is a view of, say, what a jet stream might look like. And about the jet stream, whenever it meanders, we end up with these low and these high pressure centers. Heat waves tend to form in these high pressure centers in particular. And the reason why they do is because of properties of air. When air rises, it expands and cools, but when air descends, it compresses and warms. And this is exactly what happens over these high pressure centers. Air descends and it warms. And as it warms, right, the reason why it's warming is because it is getting compressed. And this is air from high up in the atmosphere. Air from high up in the atmosphere tends to be very dry. So this is just very warm, dry air that's getting hotter and hotter as it comes down to the surface. And so as air is descending, remember clouds form when air goes up, air is ascending, it's convecting. And so in this case, because air is descending rather than rising, it means that you basically have very clear conditions. And so then that adds to the heat wave because you end up with these conditions such that the sun is just able to bake that region more or less. So we have kind of these dual impacts in the daytime and in the nighttime. So during the day, as we mentioned, we have these high pressure centers, cloud cover is decreased, you have this warm air that is descending, and a lot of radiation that hits the surface from the sun. And another major ingredient is that you have low soil moisture, generally speaking. And this is because when we have a lot of moisture in soil and in, vegetation that's kind of being released into the atmosphere, it sort of moderates temperatures. And so when we don't have that, it really can just push the temperature up really quickly, all of these other factors. And then at night, sometimes the effects or the kind of mechanisms are a little bit distinct and a little bit different. So often at night, um, essentially, if you have a very warm surface at night, that surface can cool radiatively. However, during some of these heat wave episodes, we may have conditions such that we don't have adequate cooling of these warm conditions. And so this could be because there is a little bit of very high cloud cover that forms. It could also be because as temperatures increase, we end up getting more humidity in the air as they drop overnight. And so that humidity actually helps trap that heat close to the surface. So there's a lot of conditions that can then result in these temperatures not necessarily decreasing overnight. And so that adds to the health challenges of these heat waves as they develop. So, to summarize, what are the ingredients for a heat wave? So these are these high pressure centers where air is subsiding, the soils are very dry, and temperatures then grow very high over the course of these events. It's important to note that heat waves can occur over land or over ocean. Over ocean in particular, these are called marine heat waves. In 2015, we had a major marine heat wave off the coast of, Washington, British Columbia. We called it the blob. It impacted fisheries and other ocean-dependent industries, marine aquaculture, tourism in these regions, because often you would have like fish die-offs and other things that are not pleasant at all. And so I just want to note that right now we have a marine heat wave that is developing off of the coast of California and Baja California. So this is our forecast looking later this year into the fall. And that heat wave, even though, it maybe looks small compared to the El Nino that we see below, is pretty substantial. And so it is going to have some significant impacts. The Pacific Northwest heat wave was something that happened in 2021. And this is such an interesting heat wave to look at from the perspective of, how does a heat wave play out? So this heat wave, this is looking at all temperatures every day from the 1st of June to the 31st of August over 1950 to 2020. And then in red, you can see 2021. And this is the period of time for the heat wave. It was about 5 days of just temperatures that were so outside the norm of anything that is normal in this part of the world. And once again, this was occurring in a place where many households do not have air conditioning. When I say many, I think it's the majority, especially in British Columbia. And so what happened? Well, roads buckled, power lines melted and deformed. And so there were parts of the region that did not have power. Public transit halted because some of the rail lines actually were melting. Yeah, it was pretty brutal, pretty dramatic. Um, at this time, there were over 1,000 human deaths due to heat illness and related mortality. A lot of this was among elderly in this region. The medical emergency departments were overwhelmed. And so here, this is a figure from the New York Times, essentially showing that in 2021, even though we're in the middle of a pandemic, you can just see this huge spike in hospitalizations and emergency room visits that happened during the heat wave because people just did not feel well in the context of that heat. The other really interesting thing was that this heat wave happened at a time where there were very low tides during the day. So what happened is that a bunch of marine organisms baked in the open air. And so it was about 1 billion marine organisms that were essentially cooked to death in the course of this heat wave due to these low tides coinciding with the hottest surface temperatures. Heat also increases the risk of wildfires. So, in this exact same heat wave, there was a town in British Columbia that just went up in smoke and fire. So, this was the town of Lytton, British Columbia. The temperature there recorded was 49.5 degrees Celsius. Converted to Fahrenheit, that's 121 degrees. So something that maybe you might expect in some parts of the world, but definitely not in British Columbia. And so what happened in this particular location is as some winds came in, fires just started and the entire town practically burnt. And so this is something that is a hazard associated with major heat waves that the high temperatures, the low humidity, combined sometimes with growing near surface winds, can result in just really dangerous fire weather conditions. So, definitely a hazard that grows out of some of these episodes of extreme heat. So now the question, of course, that we all want to know about is extreme heat predictable? And the fact is that it is. But extreme heat is also one of these areas where there's just so much research going on because it's actually, to some extent, we're surprised when we can predict it, which means that we don't quite understand what physics is interacting in our models to help it be predictable. And so I'm going to present a few things that help us predict it. So first of all, teleconnections from predictable modes of variability, things like El Nino, things like the MJO or the NAO, they can help create what are called blocking high pressure systems. So these high pressure systems where you have this descending air that gets heated up and then that system just sits there. These kinds of systems, they can be essentially favored by various modes of variability. And so this is one way that we get some, really long range, medium range insights into where heat and extreme heat are likely to develop. And so here, this image is from a sort of this funny, like circumglobal wave train that formed in 2023 as this El Nino was kind of blooming in the tropical Pacific. At that time, this extreme heat sort of led to these heat domes forming over three continents, which is kind of interesting. And there was this idea that it might be linked to essentially this circumglobal wave train, essentially resonating with this El Nino that was occurring or that was growing at the same time. So another way that extreme heat is predictable is through predicting soil moisture. So we can predict soil moisture through predicting temperature, cumulative rainfall, thinking about evapotranspiration, as well as the characteristics of the soil and the vegetation at a particular location. It's important to remember this is an area of very, very, very active research. And so, land surface models are relatively young in the context of, our global modeling systems. So there's a lot of work going into specifically improving how soil and vegetation models might be able to better evolve and therefore capture the conditions likely to give rise to extreme heat. And so, yeah, it's very exciting to watch as models like this get developed and integrated into our larger modeling frameworks. Climate change does increase the likelihood of extreme heat. So there's a few ways. First of all, baseline temperatures are just hotter, right? So when I have an extreme, it's going to be a little bit more extreme. In addition to this, very interestingly, climate change tends to dry out soils. This is because temperatures are really high or warmer than usual. Then we combine that with lower relative humidity, specifically over land. This is just a thing. Climate change results in aridification of land surfaces. It means that we are more likely to have times where the soil moisture is very low. And we know that those are the conditions that are conducive to the formation of these high pressure centers that just hang out and grow and sit there and create these heat domes. Um, Also note that there is a possibility that as our globe warms, that we may have more atmospheric blocking events, but please keep in mind this is an area of very active research. So I don't really want to, jump into this fray of, do we see an increase in blocking events? Do we not? I think it is still very much up in the air. And it has actually been up in the air for maybe like at least 5 years, maybe even a decade. So yeah, hopefully we're gonna see some further insights into this in terms of really understanding potentially whether the blocking high pressure systems that lead to extreme heat may be increasing as our planet warms. But I just think at this point, we don't really want to speculate. It's possible, but active research. So now I want to get a little bit into the forecast. And so it's important to, just say something about how long range weather forecasting works. With long range forecasting, we're looking beyond 14 days. We're using Earth system models. This is very distinct from weather forecasting, where we use atmosphere only models and where we have predictability up to 14 days. And so these Earth system models are very comprehensive. And note, though, that they're not magical. So, generally speaking, beyond 14 days, you cannot get day-to-day forecasts. However, you can get really good skilled week-to-week forecasts, month-to-month forecasts, or season-to-season forecasts. And so note that I said that heat waves can be, as short as 3 days. And so in the context of, say, looking forward, 3 or 4 months into the future, you can't resolve 3 days. It is just not possible. So really what we're looking for when we talk about predicting heat is really, is that month going to be normal, like much warmer than usual? And if it is going to be much warmer than usual, then, are the conditions potentially right for the possibility of creating a span of a few days where we may have a blocking high pressure center that might tend to form into a heat wave? So here's one example. So there was extreme heat at the time of the Taylor Swift Eras Tour in November 2023. So I just took a look at our forecasting system, our back test specific to 2023, and this is what I found. So essentially, about 5 months ahead, if we look at what was predicted for October, November, and December 2023, this is what was actual, this was what was forecast. So more or less, like the forecasting system in the context of the, 50th or so 25th to 75th percentiles captured the actual conditions that were much warmer than usual for that span of 3 months. Then, if we look 3 weeks ahead, you can see that, it does capture like, hey, it looks like it's going to be really warm. But you can see that the actual conditions were like much, much warmer. So the actual event itself was in the tails. And if you actually look at the 2021 Pacific Northwest heat wave, to some extent, that is the case as well, though that event was so far out in the tail that, people call it the Black Swan event, or a Black Swan event, because it is just like such a extreme event that was so far outside of what we expected. Um, so often when we think of extreme heat, it's important to like look at forecasts and say, okay, there's a chance of extreme heat. So how can we adapt in this context? So in summer 2026, I just want to talk a little bit about what to expect. So we are coming into the start of a growing El Nino. And so what this means is that many parts of our world are going to be much warmer than usual. This includes the Asia Pacific, specifically South and Southeast Asia, Australia, Central and South America, and Africa. And a lot of these much warmer than usual conditions are combined with decreased rainfall. So that decreased rainfall combined with much warmer than usual conditions are just, very, very conducive to the formation of these sort of episodes of much higher than usual conditions. In other words, heat waves. So we are in coming into a summer where huge parts of the world are potentially going to be very vulnerable to extreme heat. And this is the forecast looking over Europe over the next few months. So yeah, this is looking to next week here, looking into the context of June. So you can see warmer than usual conditions continuing. And so I think it's pretty safe to say that Europe is going to have a warmer than usual summer. And so, in the context of that warmer than usual summer, this current heat wave that's going on is probably, just the start. It is very likely that this region is going to see more episodes of, few days of much warmer than usual temperatures. In other words, heat waves. So thank you so much. Really appreciate everyone's attention. And so you know where to find us online. And if you miss us, you can always check out our YouTube channel where there's a bunch of these webinars that we've given in the past. And some of them hopefully are informative and timely, like our webinar, for example, on El Nino. So thank you so much. And if you're very interested in a long range forecast, specifically for heat or for any other hazard, let me know. Happy to tell you more about what we do, which is to predict the weather over long time horizons to help businesses and industries across the spectrum adapt to our warming world. Thank you so much.